Hey everybody, and welcome back to Linear Algebra Online. So today we're going to talk about something called partitioned matrices, and it's just like a trick to help us multiply really big matrices easier. But to start off, I want to do this kind of problem. So there ends up being a lot of patterns that show up when you do like matrix multiplication sometimes. So if you take this one and you do a bunch of multiplications, so up through, you'll see the pattern if you get to the 7th power, but if you do a squared, just a times a, you're going to get, and to be honest, I just did these on my calculator, just to do it really quick, but that's a squared, and then if you do a times a squared, which will be a cubed, right? And in matrices, you're always, you're just going to like tack on, like if you're doing powers, you just tack on another a to the left. And so here we would get -1, 0, 0, -1. If you do a times that a cubed, you would get a to the 4th, which is 0, -1, 1, -1. And then if you do a times a to the 4th, which is now a to the 5th, you get 1, -1, 1, 0. And then this is the interesting one. If you do a times a to the 5th, then you actually get 1, 0, 0, 1, which is like our 2 by 2 identity matrix. And so if you do like a times a to the 6th, it should just equal a, because this part is just like an I2, right? Which is just like multiplying by 1, and it's not going to do anything. So sometimes like there's problems where you run into, it kind of like reduces down like this, and then you can actually solve like crazy problems like this a lot easier. So if you take 2015 and you divide it, since there's like 6, actually I also wanted to say that like a here would equal a to the 7th, right? Because a times a to the 6th is a to the 7th, but we know that a to the 6th reduces to I2. So the 7th one is like the first one. So basically there's just 6 unique answers here. And so if you take a power, like 2015, and you divide it by 6, if you do that in your calculator, you get 335.83 repeating. And basically, this is like the important part. So if you think remainders, you have like 1 out of 6, 2 out of 6, 3 out of 6. And I know they're not reduced, but that actually kind of, I think, hammers home the point here. So if there was no remainder, then it would be like a it would be like the 6, 1, and it would be like an I2 matrix. If it was like a remainder of 1/6, then it would just be like a, right? If it was 2, 6, it'd be like a squared, 3, 6, a cubed, so on and so on. So this basically tells you which one you're at, and if you're good with your decimals and you know these things, this is actually 56.83 repeating. And so that means that a to the 2015 is literally the same as a to the 5th, just based on like pattern recognition there. All right, so the main thing that we're talking about today are these things called partitioned matrices. And partitioned matrices really are just like a shortcut to help us multiply a matrix out. And the idea is, as long as we really use this for multiplication, I think mostly. And so most of the time, the only part we have to think about is when we partition a matrix, we have to be careful about like how the sizes break down. But technically, you can partition a matrix like any way you want. I mean, you basically imagine these like lines cutting across, and they do have to go like all the way across or all the way down, but you could split this matrix up into this chunk right here, where it's like a 2 by 2 identity matrix, and then a 0 matrix below that, and then I'm just going to call A and B. And so I'm looking at it in like blocks, where A is the matrix 0, 0, 2, 1, negative 1, 3, and B is the matrix 1, 4, 0, 0, 1, 7, 0, 7, 2. So that's one way you could break this thing down. And typically, though, the way we do it is we're looking for like the biggest matrix we can form that's going to be easy and nice to work with. And in this case, I actually wouldn't do it this way, okay? The way I would actually do it is I've got this identity matrix that's a 3 by 3 identity matrix. It's really big. So if I partition it so that's like my upper block, it's going to make some things with calculations a lot easier. So I would look at it this way. And I didn't write it actually in here, but that's a 3. So I'm looking at this matrix as a 3 by 3 identity, and then a 0 matrix. And a 0 matrix is literally just any matrix with all zeros in it. And then B is, so maybe not to confuse, I'm going to cross that out, because that's not how I'm doing it. And then B here is the 2 by 2 matrix 1, 7, 7, 2. And then A is 2, 1, 4, negative 1, 3, 0. But this is kind of how I would partition it and break it up, because it gives me a really big block of easy kind of to work with stuff, okay? And I'm going to show you now like a problem where we actually like do it and help us do some multiplication. So kind of using the same idea as the last problem, I have, tons of ways I could partition this. I could break it up like that, and then, I could just leave it like that. I could do that, and then I could do, this right now is a perfectly fine partition, but it's not going to be super helpful because I have an identity matrix kind of embedded in here, and I want to like pull that out. So I'm going to look at the first one as just cut down the middle with, now I'm looking at it as a 1 by 2 matrix, right? So, one row, it's like a double row, but one row by 2 columns. And then I just need to make sure that whatever I break this down into, if I'm going to do the product, that it fits with the size. So whatever I do has to be 2 by something now. And so I could do just that. I could just break it up into a 2 by 1, basically. But I don't actually want to do that. I wanted to show you that you can also do this. So I'm going to break it down there too. And now I'm actually going to pull out a 0 matrix and identity matrix in this one. And then these two, just random matrices. But this would basically now be a 2 by 2, all right, instead of a 4 by 3. But that should be fine. As long as your like corresponding block sizes are correct, you should be able to do this multiplication. So I've basically just turned the problem into this. When I do A now, I look at A as, let's call it, I've already got A and B. So I'm going to call that 2, 3, 4, 5 matrix C, and then I2, all right, that's what A is. B is a 0, and I2, and then I'm going to just do, I guess, D and E. Okay, D being the like 1, negative 2 matrix. And then I can just do, matrix multiplication. So I can do, this row times this column, and then this row times this column, right? And I'm literally going to just do it symbolically first. So I would get like C times 0, okay, plus I2 times D. And then now I'm going to do the A, it's really just like one row is how you want to look at it, times the next column. So actually, I don't think I need that much space there. I'm going to get rid of that. And then, let's see. So we would have C times I2 plus I2 times E. All right. And this helps because now I can just go and do some simplification before I even do any of the multiplication. Like this is just gone because it's C times a zero matrix. This is really just D, right? This is C. This is E, right? So AB is actually just D and then C plus E. And if you do D plus C plus E, right? Let's see, you're going to get C plus E. Maybe I should do this off to the side. I'm going to erase that. So if you do C plus E, that's the one that you actually have to spend some time thinking about. It's 2, 3, 4, 5 is my C, plus 5, 4, 3, 2, which is 7, 7, 7, 7, which is nice. So now I can just go and put everything in, because D is 1, negative 2, all right? And then, maybe I'll color code it a little bit. C plus E is 7, 7, 7, 7. And if you go to a matrix, calculator or something, and you actually multiply these out, it truly is just this 2 by 3 matrix of 1, 7, 4, negative 2, 7, 7. So it's just a shortcut to help us multiply some matrices. All right, so these are two types of special, basically partition matrices, and it kind of helps to motivate the idea of what matrix multiplication truly is. So you could take a matrix and basically make a bunch of, view it as a bunch of column vectors. So I'm partitioning down, right? And so as long as B is n by R and A is m by n, then you can do AB, right? Because the n's in a sense cancel, and you get an m by R product. And if you look at it this way, okay, well, first it's important, I guess, to realize what each A, B sub I is. So A is m by n, and B is basically n by 1, right? And so if you do a m by n times an n by 1, right, these things cancel, you get an m by 1 matrix, right? So it all checks out with the sizes. You're basically just, viewing any matrix. You could view this matrix as 3 just column vectors. And when you do this kind of matrix multiplication, this is what we actually call matrix row expansion. And it basically is just a way to envision matrix multiplication more clearly as a bunch of vector dot products, because that's really what it is. It's you could view, and I'm going to talk about this in a second over here, but you can view, dot product as literally really simple basic matrix multiplication between just two super simple matrices. But this kind of is the way that we envision the complete behavior of all the dot products, kind of how they work together. And you can do the same if you partition across. So basically you can do the same for rows of A and then use B. So in this case, it's you're taking this matrix and you're splitting all of its m rows up into like m vectors, right? And then they can go on for however long n is. And then you can do, you can multiply now that a row vector kind of partition, times b, like I have right here. And then you'd get like the first row vector times b there, and then second row vector times b there. And this is, oddly enough, called row matrix expansion. And it really is just a way that we I think our brains like to see this because it lets us see that really it truly is just a bunch of dot products. And here's I'm just going to try to explain this a little bit more here. So when I write this times this, matrix multiplication wise, we literally just do 1 times 0 plus 2 times 1 plus 3 times -1. And that is a dot product, right? In this case, that equals -1. And if you just had more of these columns, right, you could just kind of partition them down and just think about it as checking the dot product along with the different vectors and then just kind of making a new matrix that encapsulates all of those dot products. There's actually something deeper going on even here too, and it would kind of take a while to fully get into, but I'm going to kind of try to explain it a bit here. So a matrix is something called a linear transformation. They're synonymous, and we're going to talk about linear transformations and matrices like back and forth this year. So you can study linear algebra just from the idea of just looking at matrices, but you can also study it by looking at interpreting a matrix as a function, basically, like a function literally written this way, where it's a linear function, which is why I'm using L, and it operates on vectors. So those are the inputs for this function. And in this situation, I just realized my arrow is in the wrong spot. Ignore that arrow. So in this situation, we take 3 variables, like we're taking something from R3. And when we do that, truly this is just dot product. When we do this, right, we end up with just the -1. So here we are sending something from R3 to R. Okay, we're doing a transformation where the domain is 3 inputs and the output, the range space, is just one-dimensional number line. Okay, and this is identical to the dot product. And since we can interpret this matrix right here, and I'm really viewing this as a matrix, since we can interpret that as a vector or a linear transformation, or I'm just going to say matrix, okay, because really they are the same thing. So this, this is like just a column vector like we're used to, but I'm saying this part right here, the 1, 2, 3, we can kind of do, let me kind of bring this down. We can either think of it as like dot product from like Calc 3, where I might write it like this. So I can think of 1, 2, 3 here as a vector, or I can think about it as 1, 2, 3 written that way, which now I'm viewing it as a matrix or a linear transformation. And so here it's dot product. Here it's matrix multiplication. They are 2 names for the same thing. And this is something in math when we see like the same concept but written 2 different ways. This is something called duality. And it's actually like a formal term. Basically, the dual, we say, of the dot product is matrix multiplication. And since these 2 things can sort of flip-flop back and forth, like we can interpret 1, 2, 3 as a vector or a matrix, so matrix being written that way, vector being written that way, there's actually a formal like matrix operation that lets me do that switch back and forth. And it's something called the transpose of a vector or a matrix. So the transpose, we use T, okay, and oddly enough, but basically the T, if you take like 1, 2, 3 as like a vector, let's say, and you transpose it, then you would write 1, 2, 3 that way. It's the way that we actually mathematically talk about that duality. It's the way that we take a vector and like think about it as a matrix. Or if I actually take parentheses around this and I take the transpose of the transpose, then these cancel. And so you can think of it taking the transpose of a matrix and getting a column vector like that. So that's a really quick rundown. There's like a lot going on here that I could talk about, but this is kind of like some deeper math definitely. But basically vectors and matrix multiplication are like synonymous. And so there's an operation called a transpose that lets me switch back and forth. And I do want to like formally define it right here. So this transpose thing that I'm talking about of an m by n matrix, because you can do it for an entire matrix, like a large matrix, not just a small one like I did, is an n by m matrix, and we denote it a to the t power, okay? And it's not really like a t power or something like, it's just the notation. So when I do a t like that, and if I use that ij notation, so I is the rows and j is the columns. If you do at ij, then that would be a ji. They basically just switch. Rows become columns, columns become rows. And I'm going to kind of go through 2 examples down here quick, but there is another really important definition that we'll see a ton this year, and that's something called a symmetric matrix. And a symmetric matrix is one where its transpose is equal to itself. So I'm just going to take the transposes of these, and some of them are symmetric, and you'll see. So if I do AT, then I need to put take this row, that row, the first row becomes the first column, all right? The second row becomes the second column, and the third row becomes the third column, okay? And if I do over here, BT, probably should have started with the easier one, but 1, 2, the first row becomes the first column, and then second row here becomes the second column, all right? So rows go to columns, columns go to rows. So if you look, this matrix, definitely not that, okay? So B doesn't equal BT, so not symmetric. All right, but over here, A equals AT, so yeah, it is. A nice thing about symmetric matrices is that there's there's symmetry, which is why we call it that. So let me actually erase this. So if you look, there's symmetry along the diagonal like that, right? So if you take any symmetric matrix, you should be able to draw this diagonal, and you should see symmetry. Like the 3 is reflected here, the 2 is reflected here, the 0 here, right? And that's just like a property of, almost, just like a geometric property. If something's rows were equal to its columns, then there would be that symmetry. So that's a quick way to check for symmetric matrices. Here, you don't have that symmetry because 2 is not -1. If it was, then it would be symmetric. So I just want to prove one problem with symmetric matrices, and I didn't skip anything, right? So this is just a quick little problem, like a quick proof to kind of show you how working with symmetric matrices is. So I'm going to start actually and prove a different problem. So I'm going to prove that A plus B, if you take the transpose of that, it's actually A transpose plus B transpose, which is kind of weird. So this is, I always think, fundamental theorem of Algebra 2. So this is what students want to do, right? But here it actually is true. So I'm going to define Aij plus Bij as Cij. Okay, I'm just saying like the sum of those is C, basically. And then if I do A plus B transpose, then this is going to equal just like Aij plus Bij transpose, which equals Cij transpose, right? So I'm just, the sum of A and B is C. And then the transpose just flips those, that order around. So then you get Cji, right? And Cji, just based on how matrix addition works, would have to be Aj plus Bji, which is just At plus Bt, right? So basically, you can actually do like the distribution thing that Algebra 2 students always want to do, where you literally can just like, if you have A plus B, all of that quantity to transpose, then it's just A transpose plus B transpose, okay? So if I want to prove this, I'm going to actually end up using this result. So there's this proof, or there's this theorem in the book that says if A is a square matrix, then A plus A transpose is a symmetric matrix. Okay? So what we need to show here is that if we take A plus A transpose and we transpose that, right, then it equals itself. That's what it means to be symmetric. So that's what I have to show. And now that I actually have this like little mini problem up here, basically this result, it's really short. So this is the proof. We start with A plus AT, and I'm going to take the transpose of it. And then we could just say by that thing I boxed up there, right? And, if I was writing out really formal, I would literally like add some words by lemma or blah, blah, blah. So if I take the transpose of a sum like that, I can, like, in a sense, distribute the transpose. And then if you do the transpose of a transpose, you just cancel, right? Because you switched the rows and columns, but then you switch back. So now this is just A. And we know that matrix multiplication is commutative. So this is the same as A plus AT. Wait, did I just say matrix multiplication? I definitely meant matrix addition. Matrix multiplication is definitely not commutative. And so then A plus AT is symmetric. And that's it. And if I had more time, I could write it out a little more formal. But hopefully that gives you a little taste of the idea of these like symmetric matrix proofs. You're going to see a lot of stuff like this.